First of all, I want to thank the organization of Materials 22 for having invited me to present here today. I will talk about one of the works of our group on the production of green hydrogen. Today's presentation is towards effective green hydrogen production by enhancing oxygen electrode kinetics with transition metals, nickel, iron, and copper, alloyed to platinum, supported on graphene nanoplatelets. So this work has been done in our group in Instituto Superior Tecnico, which is in Lisbon University in Portugal, but in collaboration with groups of some colleagues in Turkey and in Serbia. Okay, so why are we interested in hydrogen? So with this energy crisis that we are talking for some time, and now we are talking more, that we need to relieve our dependence on oil, on natural gas, and we need to find alternatives, and hydrogen appears as a very good alternative because of its high gravimetric energy density. In terms of weight, it's the material with the highest gravimetric energy density. It's environmentally friendly, it can be safe, can be used to power fuel cell electric vehicles. So hydrogen can be a very important energy carrier for the future and for now. Hydrogen can be produced by fossil fuels. Mainly nowadays it is produced from fossil fuels. Most hydrogen, about 96%, comes from all natural gas and coal and all those sources that should be avoided if we want to enter in the clean hydrogen economy. And for that, we need to produce hydrogen by using electrolysis powered by renewable energy sources. So what is in fact this concept of the hydrogen economy? So the hydrogen economy is the use of hydrogen as an energy vector to be used to power different, for example, vehicles, to generate electricity, heat. So it is consumed in different ways. Its product is just water, and we can use that generated water to have electrolysis producing more hydrogen, and we can use a renewable energy source to power as a source of electricity for that electrolysis and then close this cycle. So this is the concept of this hydrogen economy. Water electrolysis is a very simple process. It's something that we can even do at home to produce the hydrogen just with a simple source of electricity. We are able to split water into hydrogen and oxygen. But at the industrial level, there are different ways to produce the hydrogen. The two that are most are at the commercial level, it's the alkaline electrolysis and the PEM electrolysis. Alkaline electrolysis, it's a very mature technology. It is here for over 60 years and works very well. And lately, for the last few years, a lot of people is also interested in PEM electrolysis because despite being a technology a bit more expensive, it has higher efficiency. We can see that at least, for example, here in Portugal, a lot of companies are betting in the moment in alkaline electrolysis because it's a technology that really works well and can start with lower investment. As for the solid oxide electrolysis cell, this technique, this method works at high temperature and it's quite promising, but it's still not at the industrial level. It's still most of it's under research. So we are mostly interested on the alkaline electrolysis cell because it's the one that has demonstrated higher activity and higher potential because it's already implemented. The reactions are very well known. for the hydrogen and oxygen evolution in alkaline media. We have several studies where we have developed electrocatalysts for the hydrogen evolution reaction. But in fact, the oxygen evolution reaction is a bit more challenging because it involves 4-electron reaction in a multi-step reaction, and that normally involves more difficult kinetics, more sluggish kinetics. In this particular work, we are very interested in putting together our background on developing both electrodes for alkaline electrolyzers and for fuel cells. What does this mean? Like, there is a device, that can work in both modes. So this device called unitized regenerative fuel cell, which is in the heart of the hydrogen economy, can be connected to the grid, and during the night, when there is a surplus of electricity, it can work in electrolysis mode, produce hydrogen with like storing that surplus of electricity that is not being consumed. And during the day, when there is a demand for that electricity, the hydrogen can enter the same device and can be converted to electricity and feed that additional electricity to the grid. So the idea is to use this unitized regenerative fuel cell as a device that can both work in both modes and be a way to store the extra electricity during the night and give that additional electricity when it's required during the day. This is very interesting, but for the equipment for this device to work, you need bifunctional electrocatalysts. So electrocatalysts that are able to run both reactions. We are, as I said, the highest, the most sluggish reaction is the one related with the oxygen electrode, and we are focused on developing electrocatalysts that can work with good activity, so bifunctional electrocatalysts, both for the oxygen evolution reaction and for the oxygen reduction reaction that occurs in the fuel cell mode. So what we did here was to prepare a new electrocatalyst that is based on platinum alloyed with 3 different types of transition metals, with nickel or with iron or with copper. And these nanoparticles are supported on graphene nanoplatelets. So we have prepared these materials and then tested them as electrocatalysts for the positive electrode of these unitized regenerative fuel cells. That means for oxygen reduction and for oxygen evolution. So these catalysts were prepared by a simple process known as simultaneous supercritical carbon dioxide deposition technique, where the primary metal, the platinum, and the secondary metal were deposited on the graphene nanoplatelets by this supercritical simultaneous supercritical CO2 deposition, and in the same step. So here we have a scheme on how the process goes. Then we have done the characterization of these materials. They all have about 20% platinum, and the amount of the transition metal ranges between 1.4 for iron here up to 3.4 in nickel. We have done, this was measured by ICP, and we have done also TEM analysis along with the elemental mapping and the EDX spectra, and we've seen that the nanoparticle size ranges between 2 and 3 nanometers. We have also done XPS measurements of the catalysts, and here we also show the high resolution XPS scans that confirm that the materials were had the composition that we had. So as for the electrochemical characterization that we've done towards ORR and OER, we did this in an alkaline electrolyte because we want to perform this in alkaline media, and we use 0.1 molar KOH. So we evaluated the activity of the materials by determining different parameters for oxygen reduction reaction and for oxygen evolution reaction. So the number of exchange electrons that should be close to 4 if we want the direct, complete oxygen reduction reaction of this material, of the oxygen reduction reaction. We determine the Tafel slope and the diffusion limited current density. As for the OER, we determine the Tafel slope, the overpotential at current density of 10 milliamps per square centimeter, and the current density at an overpotential of 400 millivolts. We start by determining the capacitance of the materials. So this is done by scanning the potential of the materials at different scan rates. And what we do is then we check what is the difference between the positive and the negative current for each scan rate, and we plot that. So that difference that we see here from this point to this point, and we plot that as a function of the scan rate, and from that we can get the capacitance of the material. We can see here that platinum iron was the material with the higher capacitance of the three platinum transition metal alloys, and it was close to that of a platinum that we also tested, just the platinum supported on the graphene nanoplatelets. Then we did the oxygen reduction reaction studies, and for these studies, what we did is using rotating disc electrode measurements. Basically, what we do is to scan the potential at the fixed potential scan rate of 10 millivolts per second, and then we do the experiments at different rotation rates. So we increase the rotation of the disc electrode, and we have increasing currents. So we have done this for these four materials, for the alloys and just platinum, and then based on the results, we are able to plot the current that we obtain at the fixed potential value as a function of the rotation rate of the electrode. So based on that, based on this plot and using the Kutek-Levitt equation, we are able to calculate the number of exchange electrons during oxygen reduction that was close for the four materials, that was close to 4. So 4 materials behaved very well, had very good performance for oxygen reduction reaction. Also, we determined what is known as the Tafel slope, also from the curves for oxygen reduction reaction that I just showed. So here on this table, we have a comparison of different parameters that we calculate, also including the diffusion limited current density that was also higher for the platinum iron supported on the graphene nanoplatelets. So this platinum iron for oxygen reduction was the most promising material. As for oxygen evolution reaction, we also run these experiments. In this case, it's not the same approach. We don't study the effect of the rotation rate that is done on oxygen reduction reaction studies. For oxygen evolution, we scan the potential from open circuit potential until around 2 volts, and then based on these curves, we do Tafel analysis, which means a plot of the overpotential as a function of the log of current density, and from the slope of that plot, we get the Tafel slopes. Again, if we see here the lower Tafel slope, the lowest Tafel slope, which it is for the platinum iron on the graphene nanoplatelets, which is a very good result. So we want the Tafel slope to be slow, because as you see, if this is overpotential and if this is current, this means like highest increase of current for minimum change in overpotential, and that's what we want to see in practice in our URFC when we are on electrolysis mode. We also did impedance spectroscopy, and impedance spectroscopy showed us that the resistance was much lower compared to the other materials for the one with platinum iron. So you see here the much lower resistance for the charge transfer reaction compared to the other materials. As in terms of stability, they all show relatively similar stability. So just to summarize the advantages of the materials that we have prepared as bifunctional electrocatalysts for unitized regenerative fuel cells, it's very important that we believe that this simple synthesis method can be a very good approach for the preparation of the materials. So as we see here, we followed that preparation, and then we simply, I didn't show before, but we simply put the catalyst prepared on the tip of this glossy carbon electrode, then to run the measurements that I just showed. And the materials showed very good performance and stability, both for oxygen evolution reaction and for oxygen reduction reaction, especially the platinum iron supported on the graphene nanoplatelets. In fact, they showed similar activity to PTC, which is benchmark electrocatalyst for fuel cells, and at much lower cost, because we are able not only to decrease the amount of platinum, because the PTC that we compared, the commercial PTC has 48% platinum, and in our case it had 20% platinum, but also since we could have similar or better activity with about half the amount of the platinum. So at this point, what we intend to do, our future experiments are based on assembling a unitized regenerative fuel cell, because what I showed you were fundamental studies where we separately studied each of these two reactions, but we want to assemble the cell in order to be able to assess long-term stability of the electrocatalysts and also their performance in a real application. So I want to thank the funders of this work, both from Serbia and in Portugal, and thank you very much for your attention.